Hello, so I'll be talking on the deep learning applications in our data set. Our project objective is to use deep learning to detect inference at increased rates of HIE using analysis of EFM signals. So my methodology is I'm using the pre-processed. Okay, so I'm using the pre-processed FHL signals. I'm applying a time frequency resolution transformation, that's a scattering transform. I put that through a deep learning classifier and I try to get whether it's a normal outcome or an HIE intervention. So my classification experiment I did a random, I've selected all the HIE cases, that's 417, and I randomly undersampled the healthy cases from our database due to the class imbalance problem. I'm doing a 10-fold cross-validation with 5 repetitions. And I split that the training and validation I used 12 hours of signals, but for the training, when I tested between the 12 hours and the 6 hours, there was no difference in performance. So I only used the last 6 hours for computational reasons. But during the testing, I test the whole 12 hours of labor. Because we have a large data set, in addition to the cross-code validation, I also have 4,000 healthy records, which I use as a holdout test. So why am I using scattering transform? So it says time frequency resolution. Traditionally, most people use Fourier transform. That offers time invariant, but it's not stable. The wavelet transform is not time variant, but it also offers some stability. So scattering transform is trying to use the advantages of the Fourier transform with the wavelet transform to produce a time frequency resolution. On the rightmost part, I show an example of the FHL signal. That's the first one is the FHL signal. The second one is order 0. That's a low-pass filtered signal. The other one, which is the third panel, is just the frequency resolution at various time scales. So that's kind of an intensity plot. Then the order 2 is a further time scaled version of order 1. So we combine all this, order 0, order 1, and order 2 as our scattering transform coefficients with our deep learning. So my classification in summary again is I'm using the pre-processed signal. I compute a scattering transform. That's a time frequency transform of the signals. I currently use a 3-layered by LSTM layer, and I get a neural network output as a dense layer. I'm using a 3-layer LSTM. When I use the 2-layer, there was not much improvement in performance. So with some preliminary analysis, I settled on a 3-layer. I'm doing a binary classification between a healthy class and unhealthy. These are the HIE cases with an early stopping to prevent training when there's no improvement in the validation loss. So similar to my colleagues, I'm also using the cumulative recombination rate. So I did 5 iterations of each fold. The reason I did that was based on how you started deep learning, the initialization of the weights, it affects the performance. So we did 5 models for each fold. How do I select the best candidate per fold? So I computed the false positive and the true positive rate. So in classification experiments, the default classification threshold is 0.5. That's if you're above 0.5, you are labeled as unhealthy. If you are below that, you're a healthy case. So that's the labeled by the red dot. So in this instance, when my threshold is 0.5, I have a false positive rate of around 0.6. But as my earlier colleagues said, we want models that have a false positive rate that will base some clinically acceptable level. So we set that false positive rate at 30%. That's the green dot. So I now compare all the 5 models, and I choose which one gives me a higher true positive rate at that acceptable false positive rate of 30%. And from here is my candidate 2, and I'll select that to present my model. So now I go to the metrics. So I'm comparing what's the false positive rate and the true positive rate when I use the default decision threshold and then the false positive base constraint. The first result is looking at the k-fold cross-validation, the test results. The second one is using the holdout test, that's the 4,000 healthy cases. And the third plot is looking at the true positive rate, that's in the HIE cases, what's the effect. So in the left, I'll talk about the first plot. The red one shows when I use the default classification threshold of 0.5, what's the performance. Then the blue one is when I use the constraint threshold, what is the performance. So I'll talk on the first one. For the first one, I'm just showing 1-fold experiment results here. When I use the default classification rate, I realize my false positive rate goes very high. There will be unnecessary interventions and will increase the number of CS cases as compared to when I use a false positive based classification that gives me the blue instance. And I see that story in the first panel block and in the holdout sets. But there's always a compromise. So when I'm able to control the false positive rate, I see the subsequent effects on my true positive rate, which I see as the last plot. So even though I've been able to successfully reduce unnecessary CS, unfortunately this also leads to a decrease in my detection rate, but I'm still getting a detection rate that's converging to around slightly below 60% at the end of towards labor. So in summary case, we want clinically useful models with false positive rates that are below a current CS rate. And this is very important. Why is this important? So in a medical data set, we have a lot of healthy cases. So if you don't control for the false positive rate, you are going to end up introducing unnecessary CS, which presents risks to the mother and child. And then constraining the false positive rate is a good idea, but this also affects the true positive rate and then requires us to adjust the decision threshold. As we've seen, the results are not really good, so the next stage is how to try and improve the early detection rate and then explore other deep learning models. My funding agencies and then the research group. Thank you.